This section, we're going to look at the RF portion of 5G. Okay. Ask questions if appropriate on the slides. We're going to look at what is 5G, right? It's a fundamental question that I think everyone in this room knows, but I always have to go into these sessions thinking that there's people out there that are like, I've heard it on TV and I want to know more. So we're going to actually cover what 5G is. We'll do a 5G overview. We'll look at some key use cases. Danny had covered a few earlier. We kind of go into a little bit more detail. We'll look at some key 5G measurements, signal measurements. Those are over the air, and there's a reason why we're doing it over the air. We'll look at interference, and then we'll do the live demo. Of course, there'll be a break between the interference and the live demo. Okay? All right, so what is 5G? In the number of people I've talked to, a lot of people get it right. Okay? They understand that it is the 5th generation network technology, cellular technology. But others have been insistent that they've had it for a while. Because their router says 5G, they've had 5G. Now, I'm not trying to make light of this, but the reality is there's a lot of misconceptions out there of what 5G is. You know, other people think 5G is, you know, this adopted military beamforming mass control device, right? Because of beamforming and millimeter wave. And millimeter wave is kind of a new technology, or new, not really new, but new for cellular. And a lot of people are a little bit nervous about that. So we're going to look at what 5G really is, okay? And I was trying to, I'm a picture person. So I was trying to find a picture that kind of associated what 5G is, at least to me and to the people I've talked to. And with this zip line, you don't know where the end of it is, right? So we're just starting into 5G. And there's a lot of newness and a lot of concern. Yet we're going to strap on and we're going to let go. And hopefully at the end, it's not a cliff, right? And I'm not trying to be funny, but the reality is we're going to have a lot of hurdles, okay? I mean, you can already see it, right? Legislation has been passed for small cells, for things of that nature. There's been different cities that have dragged their feet on deployments because of legality issues. So I think there's a lot of hesitation. We saw some stuff in 4G, but not nearly as much because millimeter wave and some other stuff wasn't really a factor at that point. So what are the key use cases? Okay, everyone is going to be or should already be familiar with enhanced mobile broadband. What is that? 20 gigabits to a device. Now that doesn't necessarily need to be a UE, right? Some carriers are actually deploying this as the final mile instead of fiber. They're going to go over RF. And in the millimeter wave, building to building, I mean, it's been done before, right? I mean, millimeter backhaul is not new. The only difference here is it's from a phased array type solution where it can be point to multi-point. I can have one antenna array in the middle of New York City as an example, and I can hit 2 or 3 or 5 different buildings, whereas today's point-to-point microwave is pretty much, well, point-to-point. How many of you guys are familiar with a point-to-point backhaul system? Okay, those of you who aren't, it's millimeter wave or a frequency band that is literally 2 antenna dishes pointing to each other. It's point-to-point, right? 5G is going to take a massive MIMO and be able to say, I'm going to give it to you, I'm going to give it to you, I'm going to give it to you. And when you need a lot of backhaul or a lot of bandwidth, I can send all of it to you while you're not using it, and so forth. So it's efficient use, point to multi-point, enhanced mobile broadband, okay? And of course, you're going to have the people that are on the street, and they're going to have their mobile phone, and they're going to say, oh, I can download a movie in 4 seconds before I get on the metro and take my 1-hour train ride into the city. So this is also where a lot of carriers are probably going to get their ROI, right? There's going to be a lot of people that say, oh, I'll pay an extra $5 a month to have 20 gigabits, right? Are they going to use 20 gigabits? Probably not. But being able to have that data, have that information right there immediately is going to be of value to certain people. The next use case is massive machine type communication. So your vehicle to vehicle or in an environment where you have a manufacturing facility. Now the specification, and you'll see this in Danny's slide, he keeps his as kilometers. I'm an imperial person, so I said, well, what is that in miles, right? I mean, give me kilometers, that's fine. But in miles, it would be 2.5 million devices per square mile, okay? All right, what is that really? If you break that down just a little bit further, that's one device per 12 square feet, right? I can reach 12 square feet, okay? So I have one device, yeah, I have a phone. That's great. What if you had that in a whole square mile, right? Probably not going to be that diverse. It'll probably be congested like this room. So eventually, I think we'll have 5G devices where we have 2 or 3 on our person, maybe one in the laptop, one on the phone, one kind of, I don't know, heart monitor or whatever, and something else where now each person is actually carrying multiple devices. That's another area where this machine, massive machine type communication could come into play.
Does that include IoT as well?
Yes, yeah, so these would be IoT devices, absolutely would. But they would be riding on the 5G backhaul instead of 4G or 3G, yeah. How many of you guys have, and now this is release 16, I mean the primary one right now is enhanced mobile broadband with release 15. But these two right here, massive machine and URLLC, are going to be in release 16 for sure. And you know, we talked about the autonomous cars, but one of the things that a lot of marketing tends to put out there is remote surgeries, right? Is, you know, okay, yeah, okay, let's just get it out now. Everyone can chuckle and grin and all that. Will it happen? Yes. Is it going to happen tomorrow? No. Okay. And what's the environment? Tomorrow? I'm not going to be the one laying, well, hopefully I'm not the one laying there. But what does that really mean, right? I mean, everyone likes to push that out there. Low or high availability, right? Ultra reliable and low latency. So if you're in a remote surgery, right, there could be cases where it's in an environment like this, right? This is a surgical room. The doctor's on the other side of this glass. You've got a millimeter wave repeater above the patient, and that's how all the communication is happening. Do you have interference? Probably not. Is it a controlled environment? Absolutely. Is that a safe way to do something like that? Well, if it's a contagious disease and they need to operate, they don't want to be in there with them, right? So those are the environments where I think these remote surgeries are going to come in. Now, I think a lot of people, including myself, had this vision of, yeah, an ambulance comes up, they strap you into something, and then they're going to use a cell tower on the side of the road. I mean, will we get there? Maybe. I mean, we're carrying around computers in our pockets. And anyone who was around 20 years ago would have thought that was lunacy, right? But we're doing it. Okay, so will we get to a cost-effective way where we can have communication like that? Probably, but not in the near future, in my opinion. So now here are the 3 primary use cases where release 16 of the specification will actually come to fruition and allow this stuff to permeate. With a show of hands, I'm very interactive here. With a show of hands, how many of you guys have heard of all 3 of these, or at least in some marketing fashion, one way or another? Okay, so it's new to a few of you. And those of you who haven't or have seen it, then it's just a little bit of review. But it definitely builds on this afternoon, or the rest of this morning and this afternoon. All right. All right, so what frequency bands? So I mentioned earlier that millimeter wave is a primary one, and that is where you're getting a lot of your high bandwidth, right? There's a couple of reasons for that, but everything right now is TDD, right? So all of your 5G, whether it's FR1, which is sub 6, and it's funny we say sub 6 because the specification actually goes up to 7.1, right? So if you have an instrument that covers the entire band, you're good, right? No matter where you deploy 5G, you're going to be covered. This is a licensed band here between 7 and 24. There are some individuals that are talking about reusing that spectrum. If they own it, why not reuse it, right? Especially for backhaul, right? Point-to-point or point-to-multipoint backhaul. And then your millimeter wave is 24 all the way up to 52. This is all based out of the specifications. Now, everything above 40 is hasn't been really defined. And 259 was on the table, and then they kind of pulled it back, and they're reconsidering some stuff. So will this come back? Probably. Is there always going to be a demand for RF frequency reuse? Absolutely, right? Will we run out someday? I don't know, maybe. But right now, we've got all TDD for 5G. We've got our FDDs for 4G. And of course, we have some single uplinks and single downlinks that are being used in that band as well. Okay? But these are the frequencies that are being used. In building, I think you're going to see more millimeter wave. And I cover an example later, but let me get a show of hands. How many of you think that millimeter wave outdoors is going to be practical? Okay. I think I'm going to prove to the rest of you that it could be practical. And prove to the person that thinks it's maybe not so. So it's all application dependent. Okay? But it's interesting because, well, I don't want to get ahead of myself. Okay? So let's look at 5G. What is that, right? We're talking about TDD, so we have to introduce some kind of time slot, right? So I'm on the same frequency band, and now I have a number of different frame formats which include time slots. So when I have a symbol, it falls into a specific slot, okay? Now, there are 62 defined formats. There are more reserved, but there are 62 defined. And the red is going to be considered downlink, and the blue is going to be considered uplink. Now, the X is flexible, okay? Now, what does flexible mean? I know Danny touched on this earlier about dynamic allocation, right? Well, that also applies to the RF portion, right? Eventually, I don't know when, but eventually the radios will be adaptive enough where they'll be able to say, I've got a lot of users downloading, so this is the frame format we're going to use now, and we're going to shove that out, and then when that's cleared up, we'll resync, and we'll do back to a different format. So the control between the base station and the UE, or the end device, will always be negotiated. Today, it's fixed. Anybody in here working with or know of flexible that's being deployed today, or dynamic? Okay, yeah, that's typically what I get. It's primarily fixed today. So a carrier would say, look, I want to choose a particular downlink heavy or uplink heavy frame format. You know, a stadium, this might be better, uplink, right? If I'm trying at an airport, it might be downlink because people are trying to get movies and videos or whatever before they get on a plane. So these things can be controlled based on the UEs. I'm sorry, based on the geographic location and the use case. Okay? So what we'll do is we'll look at the frame structure. So we know that frame format 32 has these as downlink, 2 flexibles, and an uplink, 2 uplinks. Okay? And it's pretty balanced. I mean, more downlink than uplink. But how does that actually fit into a time, right? We're talking about time slots. So every slot, depending on the subcarrier spacing, and we'll cover that in a little bit more detail, but the subcarrier spacing in 4G is what? 15 kilohertz, right? Orthogonal OFDM. So in this example, we've got 1 millisecond for a frame. We've got 14 symbols. And we've got our subcarrier spacing at 15 kilohertz, okay? Now, what does that mean in timing? Because I am in the 15 kilohertz subcarrier spacing, my symbol times, each one of these is going to be 66 microseconds. My nominal, now the first, every half a millisecond, you get a little bit of change in the cyclic prefix, but nominally it would be 4.7 microseconds. So that looks like this. I've got my symbol, and then I've got my cyclic prefix. That happens before every single one, okay? Why am I showing you this? Timing, 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 right? If you don't get anything out of any of this besides a meal or two, it's timing is critical, right? If, and I know Danny had a slide that showed if I had 2 sites, and those 2 sites were slightly off, one would think it was at this frame, and the other would think it was at this frame, or symbol, should I say, which point it's saying, okay, there shouldn't be anything here, I'm going to ignore it. No, 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 it's downlink. I can't use it, throw it away, and now you have timing errors. That's all based on the symbol time, right? As I go down and do higher and higher subcarrier spacing, you'll notice that I get way more symbols and my timing becomes even more critical, okay? So if you were off by just, let's say, 5 microseconds, I think that's the spec, right? 5 microseconds. That throws you into a completely different symbol at 240 kilohertz spacing, okay? That's how the correlation between timing and FDD actually occur, okay? That's the resulting. Now, could you get away with a little bit sloppier timing? with 15 kilohertz spacing? Maybe, because your time requirements are different. But as you get to 240, it becomes even more critical. More data is going through at a faster rate. That also comes into play with latency, right? So we're always talking about, well, if the frame is 1 millisecond and I need to respond in 50 microseconds or whatever, how do I do that? Well, you're not relying on every single frame. You're looking at the symbols within that frame because it's time-based, okay? Totally different than FDD. So try to reinforce that because as we go through this, we're going to build. So if there's questions, the hands need to go up now so we can iron those out. No? Okay. How many of you guys have seen this before? Okay, no questions, and you haven't seen it before, so I'm assuming that I'm being clear on this, which I appreciate. So this was 1 millisecond, 14 frames. I'm sorry, 14 symbols, right? Where does that land in here? So here's that same format 32, and that would be equivalent to 1 resource there. This is frequency, okay, so this is what a spectrum, how many of you guys have used Spectrum Analyzer before? Okay, this is your RF portion, so this is time, and this is RF. I was going to rotate it, but it got a little bit more complicated, so this hopefully will be okay. And you'll notice that you've got a little bit more signal here, and we'll cover that in a minute. But all of this is your user data. And this piece of information will repeat every 10 to 20 milliseconds. And we know that this is 1 millisecond. So if you look at slot 0 all the way to slot 19, that gives you your 20 milliseconds. Okay? So this is how the 5G format is sent over the air. Okay? Any questions on this piece? All right, let me throw a question out for you. If I had an interferer that was sitting right here, right, a very strong CW signal, how much impact would it really have? Well, I would affect this entire frequency band and time slot, right? So we could go through and do the math on how much it actually would affect it. But the control and the synchronization all occur right here, and we'll get to this in a minute. So therefore, the UE would still be able to function, but it just would have a limited capability. If that same interferer landed right here within our SSB, then it would affect that, and then your timing and other things would really fall into the wayside. So where the interference lands is important, okay, or has an impact. Wideband CDMA is code division, right? Or CDMA is code division, whereas the UEs use the entire thing to get the information out. This is slightly different. So the other thing that happens, and I mentioned earlier, you have a massive array, right? And we can do beamforming, okay? Those beams will vary by frequency. So the higher millimeter wave and the more elements, the more beams I can have. The lower the frequency, the less beams I can have, simply because it's an array type relationship. So it improves propagation loss. How many of you guys are familiar with millimeter wave? Okay, so if I wanted to shoot a wave, let's say at 29 gigahertz from here to the back of the room, there's a lot of propagation loss before it gets to the back of the room. I do the same thing with 700 megahertz. It's 2 miles down the road, right? So your footprint gets a lot smaller. Now, in millimeter wave, because the elements are so small, or can be so small, I can fit a lot of them on a panel, right? Then I can take multiple elements and create a beam, and the energy from each one of those then propagates out, and you overcome a lot of that propagation loss, simply because you start with so much more power in the beginning, okay? And this is, I think, where when people hear it, they're thinking, well, what if I'm in the middle of the beam? Am I going to fall over? You know, I don't know. But I guess if you're close enough, and we'll get to some mathematical numbers in a minute, but you have a near field and a far field, right? Most of these users out here, whether it's a building or a rooftop or a UE, they're going to be within one of these beams. The UE is going to talk to the base station or the node here and say, okay, I know that I'm in one and I need to download this information, so he's going to create a beam into one and directly to that phone. Send him as much information or all the information that it needs and then stop transmitting there, right? So then basically I would turn it on, give him his entire movie in 6 seconds or whatever it ends up being. And then he's like, okay, I'm happy as a clam. And then he goes about scanning more to see if any other users need data and proceed as necessary, okay? When you have a strong signal like that, you definitely overcome a lot of signal to noise, right? If your signal is stronger, the noise can be higher, right? And then tracking. Eventually, if this user is a vehicle and he's moving, he's going to go from potentially beam 1 to beam 2 or 3. Or he's going to go up in elevation, right? It could be a plane. So at which point, the beam would have to track that user until that data was completed, right? Until his download or his upload was completed. So tracking through the beams becomes important or becomes viable. These things are not available in LTE, right? You might have massive MIMO, but you're not going to be able to have tracking beams. Any question on beams? No? All right. So where does the beam information land? The beam information is all contained within the SSB. Okay, you'll notice that I have 8 individual beams, and in the previous slide I had 8 beams described, right? So each one of these would be associated with beam 0 through beam 7. Okay? When a user is in one of those beams, they're going to get their primary and secondary sync, their broadcast channel, all of that information from one of these particular SSBs. The SSB is always going to be in the beginning before the data, and the SSB is always going to be there for timing and reference and that kind of stuff. Okay? On a spectrum analyzer, you'll notice that you've got a lot more, I guess, density here, simply because this is always there every 10 to 20 milliseconds. Okay? Because it's always there, how many of you guys have used a real-time spectrum analyzer? Okay, so how many of you used a swept spectrum analyzer? Okay, so a swept spectrum analyzer will sweep through a particular frequency range, and when it sees energy, it'll plot it onto the screen. That's the simplest way to put it. And there's a local oscillator and some other stuff. But a real-time spectrum analyzer will grab the entire chunk and process it at the same time. So sweeping kind of goes away. I mean, it technically still does some sweeping, but essentially it grabs that whole piece, processes that data at the same time so that there's no gaps in coverage. Okay? That's important because a swept analyzer or swept spectrum analyzer may sweep across this when this is not present, and therefore the signal's not there, it doesn't show up. A real-time spectrum analyzer, like you see here, will grab all of this data and be able to display it in a persistence display. Okay? Therefore, because this happens very regularly, and this may not occur as often, you get the different density and the different signal strengths out here. So when you're looking at a spectrum analyzer on a 5G signal, that's why you see what you see. Okay? Questions? Okay. So what are some of the key configurations? Those of you who have worked in 4G, you know you need center frequency for uplink, you need center frequency downlink. Well, here we just have one center frequency because it's TDD. You need to know the bandwidth. You still need to know bandwidth in FDD as well, right? Am I in a 10 meg channel, 5 meg channel, so on. But you have to know, or at least let the instrument scan for, the SSB offset. How far offset is it so that when it decodes it, it will be able to pick both ends and know exactly where that's at. If it doesn't know where that's at, it won't be able to get the sync, it won't be able to decode it, and the information will be not available. The slot format is important as well for 2 reasons. One, to know how much data you can get through if you had to calculate that, right? I'm in a downlink intensive environment, but I'm using a slot format that's uplink intensive. Well, that might be why your downlink is suffering, right? The other reason that you would want to know slot format is for interference hunting. So we had talked earlier, or I mentioned earlier, that there was one of these that was flexible, right? Or even uplink. And we know in interference hunting with FDD, you look at the uplink, right? That's primarily where your interference is going to be. So in a spectrum analyzer, how do you tell the spectrum analyzer, or can you, tell the spectrum analyzer, ignore all the blue, ignore all the green, and only give me the slot for white. That way I can see the TDD signal only when it's off. I mean, it's possible to do, and I'll walk through that. So you tell the spectrum analyzer, show me only when it's supposed to be off. I'll only know that if I know the slot format, and now I can go look for interference. Okay? That's interference hunting in a TDD world. Okay? The number of beams is important so that you can make sure you have the appropriate number of SSBs, right? And then resource block, subcarrier spacing, and then subcarriers. This is more informational. The instrument doesn't necessarily need to know that, but it can derive that information. All right, any questions on the key elements? Again, we're continuing to build, so hopefully at the end of this, when it's Q&A, it's not like, hey, what's a beam? So if you have a question now, by all means ask. No? All right. Why are we doing over-the-air measurements? CIPRI allowed you to look at the RF data, right? And I don't know how many of you guys picked this up. It's in the poster, I believe, but Danny had a slide earlier that talked about the RU, right? The DU and the CU. What was common at the very bottom of all of those slides? Your IQ data is no more. There is no more IQ data coming out of the antenna. It's all handled in the elements, the radio unit. So if you don't have any IQ data, how do you look for interference? How do you make a measurement? None of that stuff gets propagated down to the end user. It has to be done over the air. Okay? Now, there's a couple of different ways, but you want to be in the far field, right? You want to be in front of whatever beam you're making a measurement on, and you want to know exactly how far you are away. So there's devices out there, golf rangefinders and other things that can give you fairly close accuracy laser finders to figure out how far this horn antenna or the instrument is from there. You're also, in a millimeter wave environment, going to need to know the gain of this, because that's going to be critical, and you're going to need to know the loss inside your cable. Okay? Once you have that information, you can make an over-the-air measurement accurately and get an idea of several different quality metrics within that antenna. Okay? This is how over-the-air measurements need to be done. I mean, there's really no way around that. Okay? If you can't physically connect to it, you can't get the information out. So what are some of the measurements that you're going to make? You've got EIRP, right? So remember before I talked about the beam and saying, okay, I'm going to take these 6 or 4 or 5 elements and I'm going to create a beam. That beam is going to create more energy right there at the radio than it is, or I'm sorry, at the antenna than it is at the user. But I want to know how much is being put out by the radio. I have to calculate that. So from this far field, right, and I have a measurement on this, but from the far field, if I say, okay, I'm pointing right in, bore-sighted right into that center beam, the beam I'm making a measurement on, and I know I have X gain and X loss, then the instrument says, okay, based on this distance and gain and loss, that radio is putting out X number of dB or watts, right? Then you can look at the radio specification and say the radio puts out 250 watts. When I'm out there at the field, I'm getting 242 watts. Okay, it's within spec. Okay. All right. Frequency error. I mean, if you're off on frequency, it's no-go, right? Time offset. We've already talked about timing. Timing is important, so we'll make a measurement on timing. Knowing what cell you're on is going to be important. Modulation quality, even in LTE, is important. If you've got symbols that are coming out and they're modulated and they're poor EVM, I mean the radio's not going, or the UE is not going to be able to demodulate it. Therefore, your throughput is going to be 0 or very low. Occupied bandwidth. That's important if you have 100 megahertz of bandwidth and the radio is only putting out 50. Well, there's a problem there. Adjacent channel leakage ratio. This is interesting because right now you've got a transmitter that's always on. It's easy, right? You say, okay, I tuned to that frequency, but now I'm TDD. So I only make that measurement when the transmitter's on. So it's almost the inverse to interference hunting in a TDD world. And we'll cover that in more detail. But you have to think completely opposite there. Spurious noise, and then, of course, your SSB, what SSB you're on, and that kind of information. Okay? The SSB contains your primary sync signal, your secondary sync signal, broadcast channel, that kind of information. All right? Okay. So we're going to spend a little bit of time on this particular slide. Okay? Everyone hopefully can see this slide. So from a measurement perspective, we've already given it a center frequency. We know the channel bandwidth and the SSB offset. Okay? Subcarrier spacing. So these four right here, we kind of covered before. That's what the instrument needs to know. Now, whether or not the instrument derived that from scanning itself or the user manually input it like this in this particular example, it doesn't matter. You're just telling the instrument where it needs to go look. Frequency, bandwidth, time, and spacing. Once it has that, you'll get a sync and a demod. You know that you're looking at the SSB, and you know that you're demodulating it correctly. Okay? You'll know what cell groups you're on. You'll know what the frequency error is, and then your time offset. Okay? Now, this time offset is quite large. I mean, I could give you an example of all zeros, but we want to look at something that's kind of a little wonky. So we've got a large time offset here, but the frequency error looks relatively good. Okay? 0.024 parts per million is pretty good. Okay? Now we've got how many beams in here? 8 beams, right? Okay, so we've got 8 beams, and we knew in the example before that we were going to have 8 beams. Try to keep it consistent. I've got a horn antenna, and I'm pointing it at this particular beam. Okay, so I know where my strongest beam is. I can look at my signal-to-noise ratio, and you'll notice that even though you might have a strong signal, your signal-to-noise ratio may not be as correlated. Okay, so a lot of times your signal might be strong, but you could be getting a lot of reflections. Okay, so we're talking about millimeter wave. We're talking about something that's very reflective, right? I could have a base station across the street, and with the glass on this window, I get very little penetration, if any at all, right? But if I go outside in the parking lot and I put up an antenna, I might be able to point at the glass and get a signal that's almost as strong as if I pointed it right at the tower, simply because I get all these reflections coming back. So making sure that you have good signal-to-noise ratio and then drilling into that to get more information is important. Your RSRP, RSRQ are calculated too based on the information, the measurement that's being made. And these are also important because it gives you the health of your sidebands or your SSBs. Okay? So this type of measurement will give you the health of the radio, or at least that beam or set of beams that you're in. And from there, you can make adjustments, right? Is my timing off? What do I need to do? Is my signal noise? Am I getting too many reflections? And then you can start to troubleshoot from there. But having this information over the air in the field is going to be very vital. Okay? Questions? Comments? Concerns? Wow, Tom doesn't even have a question. All right, good. No, you can keep your comments to yourself. All right, so let's drill in. That was multi-beam. Now let's look at something a little bit more specific. So now we're in a single beam, and we've selected one, and we can see that the signal and noise, it's 22. It's okay, but I've got some EVM issues right here. Okay. Now these EVM, primary and secondary sync and broadcast channel, these are coming out of our SSBs, right? So our beam information is right here. RSRP is for the whole as a whole, and so is RSRQ. So this information gives you a picture of the whole, I guess you could say, beam, and then, or sorry, the whole radio, and then you're looking at the individual beam down here, or the channel. Okay. None of this has changed. Okay, we're still on the same center offset, but now we can drill in and look to see, why is my throughput so bad? Well, maybe I've got interference. Maybe this 7% EVM is because I have an interfering signal that's overlaying. Remember the picture I had earlier where I said if the interfering signal falls within that SSB band, then I'm going to have problems with my channel or my beams. That's could be potentially what I see here. Okay? If I looked at the RF portion of this, I would have to then go to an RTSA or a gated sweep and look to see, do I have interference and where is it at? Okay? I can also take this information and map it. So sometimes a user will say, look, I've got an antenna covering this parking lot. I'll just use a parking lot as an example. And I've got somebody coming into the parking lot and I've got people leaving the parking lot. I want to make sure they're covered throughout the whole parking lot, right? It kind of sounds like a weird thing, but think about it from a automation for parking, right? When the car comes in, the signal has to be uploaded, right? So we're talking about doing this wirelessly. So I can take a device, right, ours or other device, and map out how strong those beams are and the quality of those beams all the way through that drive path. So if I did that, I would know, hey, if a car follows this white line or this lane, they're going to have good coverage all the way through, right? Or what happens if one of those elements in the massive array goes bad? Well, I might get to a point where it can't form a beam, and now I've got a problem only in a particular beam. That's what you're going to be able to use this for, right? You're going to want to make sure that each one of those beams is coming out clearly and able to be used by that, the UE or the end device, okay? I mentioned this earlier, so EIRP. In this case, in this example, should I say, I've got a center frequency. I know how far I am away. I'm 120 meters away, okay? And I know path loss based on that frequency, where am I at? This frequency, is going to be about 105, right? I come down, I put in my channel gain, or my antenna gain. I know how much loss I have in that cable, and then I make a measurement. This is what my instantaneous EIRP is, and then I've got a max hold EIRP. Anyone want to take a stab at why I would have both of those numbers? Okay. This is the number that I'm concerned about, right? If I put the antenna up, right, and I go out there today, and I've got my directional antenna, my horn antenna, and I'm directly on that bore site, right, directly in the center, these numbers are going to be the same, okay? If a storm had gone through or some other thing had bumped that antenna, I said, no, when I'm here, I should be in the center. It's not, I'm going to have a lower number. So if I walk around a little bit and I change the polarization, I'll be able to do a max hold to know at some point in that projected bore site, I got that as a max hold. So that is a way, instead of constantly looking at the instrument and going, no, 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 it just holds that max value for you, okay? Which is very useful, especially if you have to validate a radio or multiple beams in a radio, okay? Questions on EIRP? All right, one other thing on EIRP. Testing the health of the radio, right? The radio is supposed to put out, let's say it's supposed to put out 40 dBm, just because that's close to 38. Okay, so I'm 2 dB, I mean, maybe I've got something wrong with my horn antenna, or maybe I miscalculated my cable or something like that. It's not grossly off, right? If it was grossly off, then I would be able to make a decision on what to do. The other factor in there is public health, right? People are concerned, how much radiation is being put out by this particular thing, because it's outside of my bedroom window, because the lamppost is right outside my bedroom window. This is another way to verify not only how much power is getting to the user, but how much power is coming out of the radio, right? I think, personally, this is just me personally, I think the public safety aspect will become more of a hot topic as 5G rolls out. 4G, not so much, because it was in the same frequency band as 3G, right? I mean, they're just like, oh yeah, it's faster throughput. But as soon as you tack on, I hate to say it, but as soon as you tack on millimeter wave, people start to get nervous. I mean, some of you guys in the room might be nervous as well. You don't have to raise your hand, I'm not going to ask you. All right? Multi-carrier verification. Some carriers will buy more than one band, so they need to verify that all of those channels are up at the same time. In LTE, that would be carrier aggregation. It's kind of similar for 5G, but this is a way to make sure that they're all at the same level and they're all being, there's no fade or anything like that inside the beams or inside the signals. Okay? That's pretty straightforward. All right, now, we've got about about 19 minutes left, and I'm going to spend a little bit more time, probably than normal, on this. So gated sweep. How many of you guys are familiar with zero span or time domain? Okay. So what we're looking at here is the time domain on a spectrum analyzer. So essentially, it's telling me what that signal or that signal strength has been over a period of time. Okay? Why do I care? Well, in a TDD world, you have to tell it where to look. So in this case, we're looking at the downlink, right? Because you remember that map that we had earlier? So I'm looking at a downlink. So if I set my power versus time to tell the spectrum analyzer only look at the downlink portion when it's on, then I can measure channel power. Okay? When I convert that, this is the next step, and we can do this in real time if necessary, or if time allows. This is what it looks like from a frequency domain. So I have my entire 100 megahertz channel here, but I'm only looking at it when the signal is on. Okay? So it's on. I can make accurate channel power measurements. I can make accurate channel power measurements. There's other ones, but in this case, it'd be a channel power measurement. Okay? Adjacent channel power. So I want to see how much leakage I have in adjacent channels only when that transmitter is on. So if you've done an adjacent channel power measurement before in an FDD world, that transmitter is always on. You don't care about gated sweep, and you just go to adjacent channel power. But in this case, we have to gate it, and then we have to set up what those adjacent channels are. And this is 100 meg. And we can see down here we've got our adjacent channel spacing, and we've got our limits set. And then we can see if we have pass or fail. And then, of course, we have lower limits, too. So this is your upper frequency limits, right? I've got 2 of them. And then down here, I've got my main, which is in the middle. And then I've got adjacent and alternate. Okay? So these upper and lower have to do with frequency, upper frequency and lower frequency. Now, if you had something that was failing, obviously you would be able to see it here. But then the question becomes, how do I know it's not interference? And it's a valid question, right? Because you could have interference kicking in at the same time. So anyone want to take a stab at how it would verify a gated adjacent channel power to verify that that's not due to interference? Oh, wrong way. What if I were to sample it right there? If I sampled it right here, then it's off. This would be off, and this would be off. But if I had something that was protruding over here or something over here, I would know that if the transmitter was off and I still saw that, it's not my transmitter. Okay? Again, another way to use another way to use a gated sweep. Okay? Spectral emission mask. This one, of course, follows the same logic, right? I would go in and do a gated sweep only when it was on, and I would put my parameters in down here, FCC requirements or whatever kind of compliance requirements were necessary. And then I would be able to see, do I pass or do I fail? Now in this example, I've failed, right? Barely, but I did fail. And so I can see right there I've got a little bit of a violation, and I think it was like right here I had a little bit of a violation. So I've got a couple of small violations, but it's still a violation, so I would have to go figure out what's going on. Okay? Questions? Okay. Occupied bandwidth, right? I've paid for 100 megahertz. My radio is supposed to put out 100 megahertz. I want to make sure I'm using that whole 100 megahertz. In this case, I am, right? I've got a span of 200. I'm making a measurement on 100, and I'm passing. Okay? Anyone want to take a stab? I know I'm driving this home, but it's important. Anyone want to take a stab at what my gated sweep was set up for, on or off? Uplink or downlink? Downlink. right? So downlink, it has to be on, right? So I have to be able to make sure that that signal's on, all right? So I know it's on, I know I'm using it. Now, I have seen, this is a little bit different because this was back in the 3G world, but I have seen where the, and you guys may have seen this as well, where you have a signal that looks like this, but then it rolls off at the end. You just have this like weird roll off at the end. Filtering on the signal didn't pass all the way through, so because the filter had a sharper roll off or an incorrect roll off, it was actually blocking part of that signal before it even left the radio. So these are ways to verify that everything is working as it should, okay? All right, interference. So we'll spend the last 14 minutes, well, probably 10 with a couple of questions on this, all right? So we'll look at a few different examples here. So here's a fast transient signal, all right? Some of you guys did see that, some of you guys did not see that. So we'll play it through a little bit slower. This is in the Wi-Fi band. You'll notice that you have signals that come in and go out, and you have one that scans all the way through, okay? If you were to watch the timing on this, it was less than a second that went through, okay? These are fast transient signals. Bluetooth, Wi-Fi, and then a scanner, okay? You're looking at an RTSA or a real-time spectrum analyzer screen with persistence. So let me explain what we're seeing here because we're going to build on this, or it's important. So we've got little blue dots, we've got darker dots, and then we've got some supposed to be red dots. I guess the projector's a little off, but it doesn't matter. We have yellow and red dots. They're like a heat map, okay? Wherever I have red and yellow, I've had that signal there more than once. In fact, I've had a signal there almost all of the time, okay? Where I have lighter blue and a little bit darker blue, that's where a signal comes on and goes off within my real-time capture only once or twice, or a very few number of times. So, in this example, we've got a persistence of 50 milliseconds and a sample of 50 milliseconds. So all of these blue dots you can think of as signals on top of one another. And the more I have on top of one another, the color changes, okay? Why am I going through all this, right? So with TDD, I'm going to have something that comes on and goes off every how many milliseconds, right? Millisecond, half millisecond? Depends. I could have symbols that come on every 5 microseconds. A swept spectrum analyzer is going to have a hard time with that. A real-time spectrum analyzer won't because it captures all of those, right? One of the things that a real-time spectrum analyzer is based in is POI, or probability of intercept. Yeah, thanks. I need to get a drink. Probability of intercept. And if you've got a probability of intercept of, let's say, 5 nanoseconds, okay? Then if I see if a signal is on for 10 nanoseconds and goes off, I'll have captured that, right? If it's 1 microsecond, and in LTE, I'm sorry, in 5G, I've got a 3 microsecond signal, I'm guaranteed to catch it, okay? So your probability of intercept is 100%, and you get a number. And you could probably see the probability of intercept up in the upper left-hand corner here. So this becomes very important when you're looking for TDD-based interference. Okay? There is one other way to do it, and we'll look at that. But this is the easiest way, I guess you could say. Okay? Oh. Questions on this? Okay. So, oh, hey, Danny. We never told him about the exam. Anyways, you'll be fine. Yeah, I know. Just kidding. So anyways, we've got a persistence right here, right? We're looking at a 5G signal, okay? What we see in the middle is probably our SSB, right? Because we've talked about how the SSB kind of resides in the middle. But you'll notice we've got some weird anomaly on the left-hand side, okay? This, I'll tell you right now, is interference. On a swept spectrum analyzer, you would most likely miss that because you would have this yellow line and then go down. So this signal, that whether or not it's on all the time or on intermittently, you would only capture when this signal went away. So I'm kind of giving away the answer here, but I know that this is a TDD signal. I don't know if this is an intermittent signal or if it's always on, but I do know that I have one piece of the equation, and that is this is TDD. Okay? So I take that same signal you just saw, I flip it over into the time domain, right? So I'm in zero span, or I'm in time domain. I've got 0 milliseconds, 1 millisecond. You remember the symbol links before for 15 kilohertz spacing utilized the whole millisecond. Do you guys remember that from, I don't know, 24 slides ago? Well, if you didn't, the example that I gave had it go all the way across. But we know that we're at 30 kilohertz spacing here. So since we're at 30, or subcarrier spacing 30 kilohertz, I've got 2 sets in that same time span. Do you guys remember that slide? I can go back. Do you want me to? How many people want to go back and look at the slide so that we can correlate this? Nobody wants to go back. All right. That's fine. You get the slides later anyways. So I go in and I look at this particular area where there's no activity, and what I actually see is that interfering signal on the side there. Okay? So I tell it, only show it to me when there shouldn't be anything there, and now I see it. Now, the other aspect to this is I'm still sweeping, right? So this is still, you know, I mean, this is not a video, but if this was intermittent, I would still see it bouncing in and out because I'm telling the spectrum analyzer, give me the gate when it's supposed to be off and show me whatever activity I have in that whatever, what was the gates? I don't have it. Whatever that gate width is, time-wise. All right? So now, without using an RTSA, I used a gated sweep, and I was able to see what was hiding underneath there. Okay? The only way that's going to work, though, is knowing what slot format should not be there, or going out there and saying, okay, I've looked at this over, let's say, 20 milliseconds or 30 milliseconds or whatever, and every time it's empty, it's probably safe to assume. Now, what happens when release 16 or 17 or whatever, and they start making this, because this is flexible, this is not unused, it's flexible. Once they start doing this dynamically, game changes, okay? But for now, it's static, and we're okay. We'll figure something out when we'll kick the can down the road until that happens. Okay? Now, another way to use real-time spectrum analyzer is looking at the subcarriers themselves. Now, we know that they're spaced accordingly, and they should have a particular shape. But with, and you can see this, with this particular trace, we can see the individual subcarriers in there, and we know if they're on or if they're off, and what their shape is. Okay? So this becomes useful for understanding what the subcarrier spacing potentially is, because you can put markers in here, or the shape of it, if there's any kind of distortion going on, and that kind of thing you can look at. Okay? This is the last slide. And in the very beginning, I asked the question, how many of you guys think millimeter wave outdoors will be successful, right? Or practical, right? Everyone remembers that question, right? So what we're seeing here is from street level, an RTSA, a waterfall, so this is basically over time, so you'll notice we have time on this side. So as that signal comes down, we notice there's a giant gap. That gap means this signal didn't make it through. Okay? Now, is this a problem? I would argue yes and no. If I was a user, okay, maybe 20 years from now, but I'm saying a user today or in the next couple of years, and I downloaded a movie, I said download, right? And I got the movie from here to here, or I started the movie download here, and I got it 6 seconds later or 7 seconds later. Am I going to say, oh, I think I dropped coverage? I really don't care. I'd never been able to download a movie in 6 seconds, and if it takes me 12 seconds, I'm still happy, right? If this is an autonomous vehicle or something critical for low latency reliable communication and that gap happens, it's no bueno, right? I mean, you're in trouble because now I'm blind for however long this is. Now, anyone want to take a stab at what that particular gap, I mean, I know there's one individual who knows what it is, but what gap caused, or what caused that gap in coverage? Semi-truck. Truck drove by, blocked the signal, truck finished going by, signal picked back up. Okay? So, if I was building top to building top, I mean, I might have a bird or a drone go by, but I could probably reliably provide final mile internet service or point to multipoint with millimeter wave outdoors. Okay? Now, if this was on a lamppost and the truck was here and I was here and the lamppost was in between us, never blocked me. So I think where I'm going with this in the last couple minutes here, it's all about application. When we think about 5G, we have to think about application. You know, a lot of people are just like, oh yeah, enhanced mobile broadband, but there are other aspects to it. And then the last thing, I promise you I'll open it up for questions if there is any, is timing, right? If you're off on timing, it doesn't matter how strong the signal is, okay? If I have two lampposts that are next to each other and I'm standing in between them, right, and I'm equally or whatever, and the timing is off, it's going to mess me up. So timing and coverage are probably the two key things I think would be the takeaway.